Antimatter sounds like science fiction, but it's real, and it's a vital component of our universe. Understanding it is one of the biggest scientific challenges of our time. In our exhibit, we'll tell you why. You'll see how we study antimatter in our experiments and how we use it every day in PET scanners. If you study matter at the very smallest scales, everything is made of the same ingredients, known as fundamental particles. Each type of fundamental particle has an antimatter equivalent, an oppositely charged particle that behaves like a mirror version. When matter and antimatter meet, they annihilate, turning all their mass into energy. But we don't see this happening very often. Antimatter is so rare that there's hardly any of it in the universe. It wasn't always like that, though. According to science's best theory of the early universe, everything started with a big bang. Back then, half of the universe was made of matter, half antimatter. Fundamental particles annihilated antiparticles, creating new particles and antiparticles in turn. This annihilation and creation continued as the universe expanded and cooled. This stopped less than a second after the Big Bang. From that time on, the universe has only contained the leftovers of those last annihilations. Because we're here, there must have been more matter than antimatter at that point. That means there must be something different about antimatter. We don't know what that difference is or why there should be one, but we must understand it if we're going to understand how we got from the Big Bang to here. In experiments at CERN, the European Organisation for Nuclear Research, scientists make and study different types of antimatter to try and understand more. LHCb is an experiment at CERN's powerful Large Hadron Collider. Here, matter and antimatter particles produced by the collider are studied and their behaviour compared.
At the LHC, we produce both particles and antiparticles. We use the elements of the LHCb detector to identify these particles. For example, as positive charged particles and negative charged particles travel through the magnetic field of LHCb, they bend in opposite directions. And we do see a difference between the behaviour of particles and antiparticles.
As well as studying antiparticles, antimatter can be investigated in larger objects. Antihydrogen atoms are formed at CERN's antiproton decelerator complex, when antiprotons are cooled and joined up with antielectrons. The ALPHA experiment studies their structure.
Antiatoms can be measured extremely precisely. We are working on measuring the energy levels of antielectrons inside antihydrogen atoms, and then we wish to compare these energy levels to those inside the hydrogen atom. On top of that, antihydrogen atoms are neutral, so we hope to be able to measure gravitational force on them, something that's not possible in any other way.
Our experiments reveal differences between matter and antimatter, but those differences are too small to explain how the universe evolved from the Big Bang to now. Antimatter is still a mystery, and we're working hard, scrutinizing our data, looking for clues that can help give us the answer. Why should you care about antimatter? If understanding the universe isn't enough, then antimatter has practical benefits too, like any blue skies research. For example, antimatter can help monitor your health. It's used in tracers for PET scanners to locate tumours, image the brain, diagnose dementia, and much else. Isn't it amazing that something so tiny and rare can tell us about the earliest moments in the universe and help improve our lives too?